I will begin with a word of prayer once I get up here. Heavenly Father, we thank you for this day. Again, I thank you for this class, for these students. Just ask you to bless our work, help us to just glorify you in what we do, and help the students ask good questions as they think of them. Lord, in your name I pray, Lord Jesus. Amen. Okay, so let me put this away. So today, I'm covering something that's important, and it's something we'll be doing over and over and over the rest of the course, pretty much. We keep using this thing. All right, so I'm going to introduce you to a calculational technique that's known as completing the square. But in order to do that, I first need to show you the problem that we're looking at, right? So what have we done so far? We've solved what kind of equations? We've solved linear equations, right? Like ax plus b equals to 0. We solved those. Then we solved two equations and two unknowns, right? We solved three equations and three unknowns. But what's up next? Well, what happens if your equation is something like a quadratic equation? What's a quadratic equation? So generically speaking, they have the following form: ax squared plus bx plus c equals to 0, right? Where a and b and c are real numbers, and a is not equal to 0. All right, that's a quadratic equation. All right, Mr. Cottrell, it's coming. Ah! Sorry, I should have given you more warning. But that marker's dead. Okay, so that's a quadratic equation. How do you solve these? Let's look at this. So example 1. What if I'm up against the equation, I don't know, x squared plus 4x equals to 0. We want to solve this quadratic equation. How should we do it? I can do this thing called factoring, right? Do you guys remember factoring? All right, so. With the square. With the square. Yeah, how about this? Can we factor anything out of this one? Yeah? Factor a what? An x, right? So x times x plus 4, right? You got a good marker? Okay, good. So x times x plus 4 equals to 0. Now, logically, why is this helpful? What is a property of real numbers? You have the product of two real numbers equal to 0. What can we say? One of them, or the other, or both, they must be 0, right? They must be 0. So this tells me that either x is equal to 0, or it tells me that x plus 4 is equal to 0. Now x equals to 0, game over, there we go, solution, right? But on the other one, I have to do a little bit more work. This tells me what? This tells me x is actually equal to minus 4. So the solution to a quadratic equation, it's not a single number, it's a what? It's a pair of numbers, right? You guys with me? Yeah? So that's example 1. Any questions about this? Yeah.
I was just going to say, can you jog my memory on the process of factoring, how we get from x squared to x parentheses x plus 4?
Oh, there is no process. That is factoring.
Got it. Okay.
I mean, there's no algorithm for factoring.
What does it represent, just distributing?
What I'm trying to say is there's no simple recipe I can tell you for factoring. In general, we just have to see it. What is factoring? Factoring is the opposite of multiplying. Yeah? Did you have something?
Okay, that opposite makes sense. It's just, this is serious.
You got it, yeah. X equals minus 4, yeah.
I'm starting to get this.
That's good.
To expand.
All right, so listen. So your question is, how do you factor? The answer is you look for common patterns. Really, the question is this. After you think you've factored correctly, are you correct or not? What do? You think about multiplying it back out, right? When I multiply back out, I get x times x, which is x squared, and x times 4, which is 4x. So I've got, that means that I factored correctly, right? So multiplying is how we check factoring. So I would say the method for factoring, at least the method I use, is guess and check. Now this works for a lot of examples, but let's go on. Yeah?
No, it's fine.
Okay, so example 2. What if we're up against x squared minus 3x plus 2 equals to 0? All right. Oh, you got it? Thank you. If you want to just pass the attendance sheet back up once it gets all the way to the back, so we can kind of make like a loop. That would be good. Otherwise, I'll lose it, and then that will be sad, because then I won't be able to answer the question when they ask me how many times you guys have missed. Yay, everyone's here. All right. So to answer your question, how do I factor this? I make myself a template. About what I'm trying to do. So here I've got x. So I put an x here. I put an x here. All right. And I think, okay, how can I factor that, right?
Oh, 2 parentheses.
Yeah, 2 parentheses. And that's right. And whatever I multiply, whatever I put here and here, right? It has to multiply to give 2, right? Multiply to get 2, right? And also what else? It has to add, or sum, you could say. Sum to what? Not 3, but minus 3. So how can we multiply numbers to get 2? You're like, well, you take 100 times 1/50th, right? 100 times 1/50th is 2. Now you're like, no, I wouldn't think of that. I'm not a nerd, right? What would you guys think? How do you get 2? Like what? -2, -1, getting straight to the point. So we either have 1 times 2 or -1 times -2, which is, you're right, that's the one. Yep, Michael?
So it's parentheses x minus 1 times x minus 2 in parentheses.
Mm-hmm. That is correct. That is exactly it. X minus 1 times x minus 2. Now, wonderful. That's factored. Now, how do we solve the problem? What does it mean if you've got x minus 1 times x minus 2 equal to 0?
Using the FOIL method.
Oh, no, that would be undoing. You don't want to FOIL it. FOILing would be multiplying. That's first, outer, inner, last. That would be unfactoring it, right? Multiplying is unfactoring. We don't want to do that. That would undo all of the hard work we just did. So instead, what we want to do is think either x minus 1 is equal to 0, right? Or what? I'm going to have to erase this if you don't. Guys, is it okay if I erase that? Poor planning on my part, but sorry. So I either have to x minus 1 equal to 0, or I have to have x minus 2 equal to 0, right? Which gives me what? In fact, x equals to 1, yay, or x equals to 2, hooray. So again, I have a quadratic equation. I have how many solutions? 2. Are there always 2 solutions? It's a trap, right? So we'll see that as we go on. All right, let's look at another example. Example 3, check this out. What if I have x squared equals to 9? How would you solve this quadratic equation? Let me slip past you here, Michael. I heard you take the square root of both sides, and what would that give you? X equals to 3. Oh, so this one's just got one equation. I mean, one solution, huh? So let's try this out. We take the square root of both sides, right? So specifically, that's the square root of x squared equals to the square root of 9. Now the square root of 9 is 3, right?
Oh, take the square root on both sides.
That's right, take the square root on both sides. That's something we can do. What is the square root of x squared, though? Is it x? What did we talk about the other day? It's not x. It's the absolute value of x. That's where you missed something. Yeah. See, that's that's right, absolute value. This means plus or minus x is equal to 3, which means that x is in fact plus or minus 3. So this illustrates what's called the square root principle. All right? If we can write something as a square equals to another number, the solution is going to be x is equal to plus or minus the square root of the number. Because we always get this absolute value thing. Is there another way we could understand this? How about factoring? We could understand this with factoring as well, right? The other way you could look at this example would be x squared minus 9 equals to 0, which factors as x minus 3 times x plus 3 equals to 0. So you see, from that perspective, it's obvious that the solution should be x equals to 3 and x equals to minus 3, right? There's my, so, but this is a sufficiently important thing. We should give this thing a name. Let's call it a theorem, all right? Theorem. If stuff squared equals to number, then stuff is equal to plus or minus the square root of the number, whatever that is. Because I don't want to do this absolute value thing every time. I just like to apply this theorem, okay? And you would too, right? Should we try it? Stuff, yeah, like whatever's there. Like here, let's try another one. Example 4. What do I mean by stuff? How about this? What if I've got like 3x plus 2 quantity squared equals to, oh, I don't know, 16. Can you solve that? The answer is yes, we can, because it's like super nice. It's already, all of the variables are already grouped in a square. That makes this like a very friendly problem. We can use the theorem. My stuff, quote unquote, is 3x plus 2, right? So by the theorem, which again is the logic we just went through in example 3, we have 3x plus 2 is equal to plus or minus the square root of 16. Did you guys get it? Now what's the solution? That we're not done yet, right? We still need to solve for x, right? So 3x is equal to minus 2 plus or, well, this is plus or minus 4, right? So minus 2 plus or minus 4, and then x is equal to minus 2 plus or minus 4, all divided by 3. So what does that give us? We get minus 2 plus 4 over 3, or minus 2 minus 4 over 3. Those are the two cases. What do we get? X equal to, I heard a 2/3, or what? Oh yeah, minus 6 over 3 is, yeah, you're minus 2. So there you go. These aren't bad, are they? No. They don't have to be pretty like this either, right? They don't have to be pretty. The answer could be complex. What's a complex number? It involves the square root of a negative number, right? So we can run into those in part of the course, like this part. So let me show you how that goes. Example 5. Before I get to that, let me do something like not quite so ugly. What if we had something like x minus 2, quantity squared, equals to, oh, I don't know, 11. How would we solve this problem? We use the theorem again, right? We use the so-called square root property. We can take the square root of the equation. We can take the square root of the equation, and what do we get? Well, we get ourselves a plus or minus the square root, right? What's the square root of 11? It's a what? Yeah, 11's a prime number. It is what it is. Like square root of 11, that's as simplified as it gets without getting a calculator and like approximating it, right? If we change it to...
Sorry, no,
I'm not, let me do one more step here. So this is x minus 2 is equal to plus or minus the square root of 11, right? Now what were you saying?
would you factor it so you separate the two x's?
Oh, factor it?
Or not factor it, separate it so that it's two separate x's, or would you leave it together?
Well, I like to use the plus minus notation while I'm simplifying things, and then at the end split into two cases. Like I did over here, I just keep plus minus and work with it, and then at the end, two cases. Is that what you're asking me? Yeah, you could, it's true, you could bifurcate, you could separate into plus and minus at this point and go down those two paths, but it's easier to kind of keep them together as a point of arithmetic, because then I just have one step to make. See, x is equal to 2 plus or minus the square root of 11. And in fact, that is a completely allowed way to write the solution. Like, they're done. End of story. That's the answer. Now, the square root of 11 is somewhere between the square root of 9 and the square root of 16. The square root of 9 is 3. The square root of 16 is 4. This is probably about 3.4, something like that. So I'm looking at 2 plus or minus 3.4. I've got one negative answer. I got one positive answer. I'd have to get a calculator to do better. One of the reasons well, let me shut up about that. One thing at a time. So that, are we good? All right, I'm censoring myself. So next up, what if we had, oh, I don't know, x plus 3 squared equals to minus 9. All right. The square root property still holds true, even when you've got a negative number there. So we get x plus 3 is equal to plus or minus the square root of minus 9. Now the square root of minus 9 is a weird thing. Maybe you haven't thought about this before, but that's the imaginary number. So like the way to simplify square root of minus 9 is like this. Square root of minus 9 you can think of as like the square root of minus 1 times 9. And then it makes sense to say this is the square root of minus 1 times the square root of 9, which is, of course, this is 3, right? So we get 3 times the square root of minus 1. Now the square root of minus 1, since about like 1777 or so, has been denoted by I for imaginary number. So instead of writing square root of minus 1, we write 3i. So the answer is really plus or minus 3i. I is the imaginary unit. Now, by the way, if I was asking you to find a real solution to this quadratic equation, at this point you should tell me there's no solution, right? The solution we're finding right now is called a complex solution. It's a complex number. In particular, we're getting x is equal to minus 3 plus or minus 3i. And that's the solution for this one. All right? Yep.
Is there any reason you wouldn't write it separately with plus minus? Like here you split the plus minus into 2/3 and -2?
Not really. No, I mean,
Same or is-
yeah. You could write more if you wanted to.
Okay.
Certainly. We could express this also as x is equal to 2 plus the square root of 11, and x is equal to 2 minus the square root of 11. This one we could split into x equals -3 plus 3i, and x is equal to -3 minus 3i, and put a box.
Difference between those forms at all, or no?
I mean, I like the plus or minus because it's lazier. But it kind of depends on the question. If the question involves graphing both roots later, then you like to know where both are, right? And if you're graphing something, then it pays off to like use a calculator to find the decimal form of these so that you know where they are, right? Because if you're like me and you look at 2 plus square root of 11, you're just kind of like, well, but then if you think, oh, wait a minute, square root of 11 is about 3.4, well, 2 plus the square root of 11 is about 5.4-ish. And, you know, if you're graphing something where you also have like the numbers 2 and 5 on that, well, you know how 5.4 relates to, say, 2 and 5 or other numbers, right? Whereas these kind of exact forms are not as helpful for graphing. But they're also exactly correct, which is, you know, that'll make your math instructor happier. But anyway, any questions? All right, so moving on. The question then is, well, what if your problem doesn't come all nice and pretty prepackaged for you? How do you deal with it, you know? And that brings us to the technique which is known as completing the square. So I'll do it in the middle board. Now, there really are two, you guys will see them as two separate uses. I see them as the same use because that's how I think, but you might see them as two different uses. There's completing the square, which allows us to factor. There's completing the square, which allows us to solve equations, all right? I would say that they're really two sides of the same coin. So I'm going to show you by example, all right? Okay. X squared plus, I don't know, 10x plus 1. Well, let's say -3 is equal to 0. Suppose you want to solve this. So what's the first order of attack? The first order of attack is always factoring. Can you factor this? So you guys try to factor it while I'm moving the camera. See what happens. So like think about 3. 3 factors is 1 times 3, right? Is there any way you can get like 1 and 3 to add up to 10? You can't do it, right? I mean, we can't factor it actually, that's the point. You can try, but you won't be able to factor it, all right? So we need another method, and this is the method. So what we do, all right, I'll allow it. You take the coefficient of b, the thing that's the coefficient of x, you take that, you divide by 2. And that gives me x plus 5. You take that, and you square it, right? Let's think about this. What is x plus 5 squared? Well, x plus 5 squared is x squared plus 10x plus 25. If you don't see that, write it down, x plus 5 times x plus 5, and FOIL it out, right? First, outer, inner, last. You get x times x, which is x squared. You get 5x plus 5x, which is 10x. And then you get the 5 times 5, which is 25. Do we agree? We agree, right? You must agree. Conform. All right, sorry. So then, look at this. What do we have? Here, we have x squared plus 10x, right? We also have that here. What happens if we solve for x squared plus 10x in the equation above? We have x plus 5 squared minus 25. Do you guys agree? X squared plus 10x is x plus 5 squared minus 25. Now, how does this help us? Because we can take what I just wrote in purple and we can use it to make the equation at the top in a nice form. So let's use it. Plug that in to the top equation. So I take this, right? And I plug it in up here. And that gives me the following. It gives me x plus 5 quantity squared minus 25 minus 3 equals to 0. Is this good? Well, this is very good, right? Because now what can we do? We can rewrite this as what?
You can factor it with the minus 28.
Yeah, we can rewrite this as x plus 5 quantity squared, right? Equals to, see this is minus 28, add it to the other side, 28, right? Hey, now we've got squared equal, the squared problem, right? Now we can go back to my theorem that I erased, right? Take the square root of both sides. We get what? X plus 5 equals to plus or minus the square root of 28, which then gives us x is equal to minus 5 plus or minus the square root of 28. Now, I don't want to go through the logic of completing the square every time we do it. So let me just write it down as an algorithm for you guys, okay? So here's the algorithm. We have x squared plus bx plus c equals to 0. We take that and we write it as x plus b over 2. You square that, and you subtract b over 2 squared plus c equals to 0. That's it. This right here is completing the square. If I say use completing the square to do something, I'm saying you make this step. That's it. It's not more complicated than that. That's it. Let me put a big bubble around it. Bubble. This pattern is completing the square. All right? Now, since I began this talk with factoring, I'd like to explain to you now, I'd like to explain to you why you couldn't factor this problem. I want you to understand why it is that you couldn't guess how to factor this problem. And I want you to appreciate that completing the square fixes this for you. So there's something I need to share with you, though, before I can make that point decently, which is that there's a standard form for factoring we need to know about. And it's this. If we have big A squared minus big B squared, anytime we have this pattern, anytime you have a difference of squares, look for this pattern. If you have that, we know how to undo it. This factors like this. A plus B times A minus B. So this is like, this is big. We need to look for this. We need to use this. This is life. All right? I mean, this is life's blood in here. Like, look for this, use it. Let me show you how that pops up over here. So if we look back to my completing the square step, right? See what happens here? We've got x plus 5 squared minus 28 equals to 0. Now you say, well, that's not the pattern. That's not a squared minus b squared. How can I make 28 a square? How can I make 28 like a b squared? What do I make b? I make b equal to the square root of 28. See, this is just a matter, you just got to use your imagination. This is exactly the square root of 28 quantity squared. All right? It's the square root of 28 squared. That is the pattern a squared minus b squared, which means I can use this idea right here to factor this. just like this. X plus 5 plus the square root of 28, x plus 5 minus the square root of 28 equals to 0. That is how this quadratic factors. And that's why you couldn't guess how to factor it. Because it is true that it factors, but it factors in an ugly way, right? It's quite hideous, is it not? But now, if you look at this, if you set these equal to 0, what do you get? Minus 5 plus or minus the square root of 28. Those are the places which make this 0, right? There's always this like dual relation between the factored form and the zeros. They're off by a minus. We've seen that in every example. I had x plus 4 in the first example. I got x equals to minus 4 as the place where it's 0, right? We got to watch out for this. Anyway, listen, we're going to do lots more of this. This is just my, opening. Now, if you might say, completing the square, why is this completing the square? That's like a really weird thing to call this, right? And I used to think it's just because you're grouping all the variables into a square, but there's actually a historical reason that's kind of interesting. And I sent you guys a link to a video which is about 20 minutes long by a fellow on YouTube, is Veritasium, I think is his channel. And he did all kinds of interesting videos. Like he's got another one about like plasma from microwaving grapes. Try it out. They're just the right, they're resonant with the frequency of the microwave, which is about 2.3 centimeters. So a typical grape is about like that. So you get standing waves in a grape, it'll blow it up. It's pretty awesome. You guys never tried microwaving grapes? You don't like your grapes hot? No, me neither. Although I do kind of want to go microwave some right now that I'm talking about it. But anyway, in that video, he actually explores the history of the complex number system and how we discovered them, how mathematicians discovered them, and all kinds of like pretty cool medieval math dual junk. And also in that video, he actually has a demonstration of how why this is called completing the square in terms of making a square from an equation. It's pretty neat. So if you watch that, you'll see that. But anyway, I don't know I really don't know how to test on that. I'm just for your giggles, you can go watch that if you want. Let me slip past you. So let me get you started on your quiz.